In a quiet corner of New South Wales, Australia, a hill perpetually smoulders from within. What looks like an unassuming rise in the landscape hides a remarkable secret beneath its surface. A coal seam burning continuously for millennia. Wisps of sulphurous smoke curl from fissures in the ground, and the earth underfoot grows warm. Hints of an ancient fire that refuses to die. This is Burning Mountain, known to the local Wanneroo people as Winjin, meaning fire. In the grand measured voice of time, we embark on a journey through the epic story of this ever-burning mountain, a slow drama unfolding across epochs. Don't forget to click on that subscribe button, hit the bell icon, and like this video, as it's the best way to support this channel, and if you enjoy it, consider sharing it around. To understand Burning Mountain's origin, we must travel back nearly 250 million years, into the late Permian period. At that time, this region was not dry bushland, but a vast swampy forest, at the edge of an ancient coastline. Great rivers once coursed here, depositing silt and sand into a lush delta. Towering tree ferns, primitive pines, and giant horsetail plants thrived in the waterlogged earth, living and dying in endless cycles. Over countless generations, their thick layers of dead plant matter were buried in mud and lacking oxygen, slowly compressing into peat and, with deeper burial and time, transforming into coal. By the end of the Permian, a seam of coal several meters thick lay entombed under sediments, the preserved bounty of that primordial swamp. The Earth did not remain still after the Permian. Over the tens of millions of years that followed, tectonic forces gently folded and uplifted the strata in this region. Layers of rock that once lay flat were tilted and raised as Australia's landmass shifted. In the upper Hunter Valley, younger rock layers that had blanketed the area, sands and clays from the Triassic period above, were gradually worn away by erosion. Wind, rain and time chiseled the landscape, exposing the ancient Permian coal bed that had been buried deep underground. What was once a subterranean secret eventually reached the surface in places, peeking out of hillsides and creek banks as dark outcrops of coal. By the time humans first walked these lands, the coal seam at Mount Winjin lay close enough to the open air that only a thin layer of soil and rock kept it hidden. The stage was set for an extraordinary ignition. No one knows exactly when the fire in Burning Mountain began. It started long before any written record, perhaps thousands or even tens of thousands of years ago. And how does a mountain catch fire? Scientists have pondered this mystery, and several theories have emerged. One possibility is a lightning strike or bushfire in ages past. A stroke of lightning or a wildfire could have ignited an exposed piece of the coal seam, starting a fire that never fully died out. Another theory suggests spontaneous combustion deep underground. The coal here is laced with minerals like iron pyrite, also known as fool's gold, which can oxidize and produce heat. Perhaps in a dry spell, the seam slowly heated itself to the point of ignition. With oxygen seeping in from the cracks at the surface, a slow burn could have taken hold. Whatever the spark, by the time the Wanneroo people knew this place as Winjin, the underworld fire was already alive, a hot ember buried in the earth, quietly feeding on the coal of the mountain. Once lit, the fire would have smouldered steadily onward. This is not a raging inferno with towering flames, but a subterranean ember that creeps through the coal seam. There were likely times it dwindled, starved of air or fuel, and times it surged when conditions were just right, but it never completely went out. The first European settlers to see it, in 1828, mistook the constant plume of smoke for a volcano, not realising they had encountered a far stranger phenomenon, the oldest known underground coal fire on the planet. By 1829, geologists understood it was the coal itself burning, part of a 235 million year old Permian coal layer, fueling a fire that had already been active for at least 5 or 6 millennia. The eternal flame had been lit, and it has been quietly burning ever since. Descending beneath the surface in our imagination, we enter the realm of the Burning Mountain fire. 30 meters below ground, where sunlight never reaches, a volume of coal is glowing red hot, like the heart of a vast furnace. The combustion here is smouldering, not flaming. A slow, low oxygen burn. It is as if a giant bed of charcoal embers were buried under the rocks, radiating heat. Within the burning seam, temperatures reach astonishing levels, on the order of 1000 degrees Celsius in the hottest spots. In some pockets, it may climb higher still, creating a blast furnace effect that can exceed 1200 degrees Celsius and even approach 700 degrees Celsius in temperature. At such heat, the very rocks are transformed. The overlying sandstones and claystones are being baked like pottery in a kiln. Clays harden into a porcelain-like mineral called alight, and some rocks fuse into brick-like red clinkers along the fire's path. The underground fire is literally remaking the mountain from the inside, leaving behind a trail of thermally altered rock and ash. Above ground, the evidence of this hidden inferno is subtle but unmistakable. You might notice the earth become warm beneath your feet, and see thin tendrils of smoke seeping from long cracks in the soil. Yellow-white crystalline deposits crust the ground, not ash from flames, but minerals like sulfur, gypsum, and alum that have steamed out of the burning coal and condensed at the surface. The air carries a faint smell of sulfur, reminiscent of burnt matches, signalling the presence of subterranean fire. The landscape itself bears scars. Trees and grasses vanish in the immediate vicinity of the fire's current location. The soil bleached and reddened by heat. The ground has a buckled, uneven look, where it has sagged into voids left by burnt-out coal or been heaved by the expansion of baked rocks. It is a scene at once ordinary in appearance and utterly unique. An ecosystem overturned by a fire that moves unseen below. A slow rearrangement of Earth driven by heat from within. Despite its destructive force, the burning mountain fire advances with glacial patience. As the coal is consumed, the fire front inches forward, feeding on fresh fuel. It creeps southward at about 1 metre per year on average, so slow that an observer standing by would perceive no movement at all. Yet over the years, those metres add up. The mountain is effectively alive with fire, its combustion constantly chewing through new coal, causing the ground to crack open ahead of it. Each crack that forms acts like a chimney, funneling oxygen down to the glowing coal and allowing the fire to sustain itself and move forward. In this way, the blaze creates its own ventilation system, forever carving a path forward. Nothing on the surface can quell it. Rain only turns to steam against the hot rock, and soil only insulates it. The fire is dug in for the long haul, locked in a balance with the mountain that shelters it. The burning mountain fire is almost inconceivably slow, and yet relentless. A single year's progress is barely a few steps' length, but after centuries the fire has travelled on the order of kilometres. Geological surveys and local observations have traced a charred, ash-laden path about 6.5 kilometres long through the mountainside, marking the route the fire has taken since its ignition. From this, scientists estimate that the coal seam has been burning for at least 5,500 to 6,000 years. To put that in perspective, if the fire began 6 millennia ago, it was already alight while humans were building the first cities of Mesopotamia and ancient Egyptians were raising the pyramids. All of recorded human history has unfolded in the time it took this hidden fire to slowly tunnel its way through the coal under Wingen. It is a drama of deep time, an ongoing saga that vastly predates the modern world, yet continues into our present day. Amazingly, Burning Mountain's story may be only just beginning. The coal seam that fuels it is part of a substantial Permian deposit stretching through the Hunter Valley, and no one knows exactly how far the fire can travel or how much fuel remains. There is every reason to believe this underground blaze could continue for many thousands of years more. As long as coal and oxygen persist, the flame will keep advancing, metre by metre, indifferent to the passage of time above. Some speculate that the fire could persist for tens of thousands of years into the future, essentially for as long as it takes to exhaust the coal or until some major geological change snuffs it out. In essence, Burning Mountain is a self-sustaining, eternal flame on a geological timescale. It has no natural ending in sight, outliving empires, and likely to still be burning long after modern civilization has turned to dust. Standing at the smoky summit of Burning Mountain, one can feel the profound passage of time and the power of Earth's hidden forces. Here is a fire kindled in our planet's ancient past that still lives today. a flame that links us to deep time, bridging a gulf of ages. In the grand story of Earth, Burning Mountain is a unique and awe-inspiring chapter, part furnace, part volcano, part time capsule. The mountain's ever-burning coal seam reminds us that Earth is not a static stage, but a living, changing system, with chemical reactions and tectonic movements that can play out over millennia. I hope you found this as interesting as I did, and as always, thanks for watching. Stretching across 350 kilometres of Western Australia's remote outback, the Devonian Great Barrier Reef stands as a fossilised relic of one of Earth's most extensive and diverse ancient ecosystems. Approximately 375 million years ago, this area was a warm tropical coastline, home to a sprawling reef system that rivaled today's Great Barrier Reef in size, complexity, and ecological importance. Preserved as rugged limestone ranges, this ancient reef offers profound insights into the evolution of marine ecosystems, the intricate interplay between life and geology, and the environmental changes that ultimately led to its demise. Now, there is a fantastic website that explains much of what is mentioned in this video. I'll include a link to it in the description. The Devonian Period is known as the Age of Fishes, due to the remarkable diversity and evolutionary advancements of fish during this period. The Devonian Great Barrier Reef was born during the Middle Devonian Period, around 385 million years ago, in a time of high global sea levels. Situated near the equator at the time, northern Western Australia's warm shallow seas provided the perfect environment for reef development. Tectonic forces shaped the Fitzroy Trough, a fault-bounded depression that opened into the Paleotethys Ocean. This basin became the foundation of the Leonard Shelf, a carbonate platform that served as the structural and ecological base for the reef's growth. Unlike modern coral-dominated reefs, Devonian reefs were built by calcareous sponges, calcified microbial mats, and calcareous algae. Tabulate and rugose corals also contributed, particularly in the early phases. Tabulate corals are extinct colonial corals with horizontal internal plates, common in Paleozoic reefs. Rugose corals are extinct solitary or colonial corals with a horn-shaped skeleton, and were major reef builders in the Paleozoic. Over millions of years, these reef builders formed platforms rising hundreds of meters above the seafloor, creating an ecosystem of immense scale. This ancient reef system was not just a singular entity, but a dynamic network of environments. In the back reef platform, protected lagoons flourished behind the reef crest. These lagoons, nutrient-rich and shielded from open ocean waves, were home to diverse communities of stromatoporoid colonies, microbial mounds, and oolitic limestones. To explain, stromatoporoid colonies are fossilized marine sponges that formed layered calcareous skeletons, contributing to reef structures. Microbial mounds are sedimentary structures built by communities of microorganisms like cyanobacteria, trapping and binding sediments, and oolitic limestones are sedimentary rocks composed mainly of ooids, small spherical grains formed by the concentric precipitation of calcium carbonate around a nucleus, typically in warm shallow marine waters. This nucleus can be a sand grain, a shell fragment, or a tiny piece of organic material. The reef margin or crest mark the high energy zone where stromatoporoids and calcareous algae built wave-resistant structures. These reefs acted as barriers, protecting the back reef zones while also serving as the structural backbone of the ecosystem. Beyond the crest lay the forereef slope, where debris from collapsing reef sections accumulated. This zone was characterized by talus deposits, turbidic sediments, and large rock fragments transported downslope. Talus deposits are accumulations of broken rock fragments at the base of steep slopes or cliffs, formed by weathering and gravity-driven processes, and turbidites are underwater landslides that deposit turbidic sediments. Further offshore, the basin collected fine sediments and preserved fossils, showcasing the interactions between the reef and the surrounding marine environment. As always, we need to look at the geology of the region, which ties directly into the formation of the reef. The development of the Devonian Great Barrier Reef was closely tied to tectonic processes in the Canning Basin. During the Middle to Late Devonian, the Leonard Shelf, located along the basin's northern margin, experienced significant crustal extension. Crustal extension is the stretching and thinning of the Earth's crust due to tectonic forces, often forming rift valleys and basins. Faulting created accommodation space, enabling the reef system to grow vertically and laterally over millions of years. These tectonic processes were instrumental in shaping the reef's architecture. Active faulting along the Fitzroy Trough influenced sedimentation patterns and allowed for the formation of steep reef margins. Marginal slopes where talus and debris accumulated reflect the dynamic interactions between tectonics and reef building processes. Faulting not only shaped the reef's overall structure, but also caused localized collapses along the reef margin. These collapses resulted in massive debris flows, which contributed to the formation of breccias and turbidic deposits in 4 reef environments. Breccia is a coarse-grained rock composed of angular fragments cemented together, formed from the collapse or fracturing of rocks. Early fractures, possibly triggered by earthquakes, led to the formation of Neptunian dikes. Neptunian dikes are vertical fractures in rocks often filled with sediment or minerals, often formed underwater. These features are common along the reef margins and prove the interplay between tectonics and sedimentation in creating complex depositional systems. The Devonian Great Barrier Reef supported a thriving ecosystem that mirrored the complexity of modern coral reefs. Stromatoporoids were the dominant reef builders, their massive calcareous frameworks stabilizing the structure. These sponges, some of which grew up to 5 meters in diameter, displayed remarkable longevity and regenerative abilities, with lifespans extending up to 500 years. Microbial communities also played a critical role in reef development. Forming structures called microbialites, these organisms created calcified mats, mounds, and domes that acted as sediment traps and contributed to the reef's growth. Similar to the stromatolites found today in Shark Bay, these microbialites were vital to the reef's stability and productivity. In addition to stromatoporoids and microbialites, tabulate and rugose corals added to the reef's diversity, especially during its early stages. Over time, these organisms declined, and by the late Devonian, microbialites and algae had become the primary reef builders. The reef was also home to a variety of marine animals. Placoderms, armoured fish with bony plates, were the apex predators of the Devonian seas, preying on smaller fish and invertebrates. Other marine life included sharks, lungfish, ammonoids, and brachiopods. Fossils of these creatures, preserved in the Gogo Formation, provide extraordinary insights into the biodiversity of the Devonian seas. The exceptional preservation of these fossils, including soft tissues and reproductive organs, makes the Gogo Formation one of the world's most important paleontological sites. Over its 23 million year history, the Devonian reef system underwent significant changes, adapting to environmental and tectonic shifts. During its initial growth phase, the reef thrived in response to global sea level rise. Tectonic subsidence created new accommodation space, allowing the reef to grow vertically and expand laterally. Tectonic subsidence is the sinking of the Earth's crust due to tectonic forces. However, the reef's ability was periodically disrupted by short-term drownings caused by rapid sea level rises. Despite these disturbances, the reef demonstrated remarkable resilience, recovering and resuming growth after each event. Around 372 million years ago, the Frasnian-Fomenian extinction event triggered a dramatic decline in stromatoporoids and other primary reef-building organisms. This event is one of the largest mass extinctions in Earth's history and coincided with global glaciation and other environmental stresses. This global crisis caused significant environmental shifts, including widespread cooling and reduced oxygen levels in marine environments, forcing the reef to adapt. The extinction's impact is vividly preserved in the fossil record of the Devonian Reef, as assemblages shifted from diverse stromatoporoid-dominated ecosystems to microbialite-rich structures. These changes reflect the reef's struggle to adapt to increasingly challenging conditions, marking a turning point in its long history of resilience. The final collapse of the reef system occurred during a period of sharp sea level regression linked to the ice age that the Earth had undergone during this time. Sea level regression exceeded 80 meters between 365 and 363 million years ago, exposing much of the reef to erosion and environmental stress. This regression, coupled with a broader cooling trend as Gondwana drifted southward, reduced the tropical habitats necessary for reef survival. When sea levels finally rose again, the reef was buried under sediments, marking the end of its existence as a living system, its vibrant life replaced by a fossilized legacy. The reef system underwent significant compaction and diagenesis, processes that left a lasting mark on its geological structure. Diagenesis involves chemical and physical changes transforming sediments into rock. In areas where early cementation had not destroyed primary porosity, compaction caused considerable reduction in thickness. Stylolithization, a process where pressure dissolves minerals at grain boundaries, created distinctive seams and reduced porosity further. Dolomitization, although not extensive, altered parts of the reef system. This is a process by which limestone is transformed into dolomite through the replacement of calcium with magnesium in the mineral structure, typically by magnesium-rich fluids. This process replaced the original limestone with dolomite in certain areas, especially in the back reef and platform margin deposits. In some cases, this enhanced secondary permeability, creating moldic porosity that has implications for the reef's potential as a hydrocarbon reservoir. Moldic porosity is a type of porosity formed when minerals or fossils in a rock dissolve, leaving behind voids or molds of the original structures. These diagenic processes highlight the post-depositional transformations that shaped the reef long after its formation. Following this, the reef was uplifted by tectonic forces. The main uplift of the Devonian reefs in the Canning Basin occurred during the late Carboniferous to early Permian, 320 to 280 million years ago. This uplift was due to compressional tectonics associated with the assembly of the supercontinent Pangaea, which created faulting and folding in the Canning Basin. A second period of uplift occurred during the Cretaceous period, approximately 140 to 100 million years ago, when renewed tectonic activity along fault zones caused further elevation and exposure. This period of uplift is associated with rifting and tectonic adjustments as Australia began to separate from Gondwana. And thus, today, the remnants of the Devonian Reef are etched into the landscape as rugged limestone ranges. These formations, shaped by millions of years of erosion and glaciation, offer a glimpse into the reef's ancient topography. During the Carboniferous Ice Age, glaciers scoured the reef, creating karst features such as caves, sinkholes, and sharp ridges. Subglacial meltwater dissolved the limestone, forming subterranean corridors and lakes. In the last 50 million years, weathering and erosion have further transformed the landscape. The Devonian Great Barrier Reef is recognised as a site of national and international geoheritage significance. Protected as geoheritage reserves, these locations are valued for their scientific and educational importance. They provide researchers with a unique opportunity to study ancient reef ecosystems, their responses to environmental changes, and their parallels with modern reefs. Preserving these sites is essential for understanding the history of Earth's biosphere and for drawing lessons about the fragility of reef ecosystems in the face of environmental stress. And so, this is the story of the Devonian Great Barrier Reef. I hope you found this as interesting as I did, and a big thank you to Steve Watts for bringing this to my attention. And as always, thanks for watching. The sun rises over Kings Canyon, its golden light spilling across the immense sandstone walls that stand sentinel over the ancient land. These towering cliffs, etched with the whispers of deep time, are not just stone, they are pages in a book of Earth's history, stretching back hundreds of millions of years. To walk among the canyons and gorges of Wataka National Park is to step into a story written by the patient hands of water, wind, and fire, the great forces that shape this timeless cathedral of rock. The foundation of Kings Canyon was laid long before the first breath of humanity, back when Australia was unrecognisable, a mere fragment adrift in a world teeming with life unfamiliar to us today. Some 500 million years ago, in what is now known as the Amadeus Basin, vast shallow seas stretched across central Australia, teeming with early marine life. These waters carried fine-grained sediments, grains of quartz, minerals and silt that settled onto the seabed. Over millions of years, layer upon layer built up, forming what we now call the Carmichael and Morini sandstones. Each layer, pressed down by the weight of new deposits, slowly compacted into rock, capturing traces of ancient rivers and shifting dunes. The Morini sandstone, which forms the towering walls of Kings Canyon, was once part of a massive coastal dune system, sculpted by relentless desert winds and shifting tides. But the world does not stand still. Over time, the seas withdrew, leaving the sedimentary layers exposed to new forces. Pressure, heat, and the inevitable hands of erosion. Don't forget to click on that subscribe button, hit the bell icon, and like this video, as it's the best way to support this channel. And if you enjoy it, consider sharing it around. The Great Alice Springs Orogeny, a period of mountain building between 350 and 300 million years ago, set in motion the forces that would one day sculpt Kings Canyon. As tectonic plates collided, the land crumpled and folded. The once horizontal layers of sedimentary rock buckled and rose, creating the George Gill Range, a landscape of high plateaus and deep fractures. With the uplift came vulnerability. The immense sandstone cliffs, standing high above the plains, were exposed to wind, rain, and temperature extremes. As water found its way into cracks, it began the slow, meticulous work of shaping the canyon. Over millions of years, small fractures widened, and whole sections of rock collapsed. The mighty cliffs we see today were carved from this process, an ongoing symphony of destruction and rebirth. Erosion is the silent architect of Kings Canyon. Every day, in ways almost imperceptible to the human eye, it continues its patient work. During the wet season, torrential rains carve deep channels, sending torrents of water cascading through the gorges. The Garden of Eden, a lush refuge nestled within the canyon's depths, exists because of this cycle. Rainwater gathers in its rock pools, sustaining life in an otherwise arid environment. This oasis would not exist without the relentless work of erosion, which scooped out depressions in the rock over countless millennia. Temperature fluctuations also play their role. The baking heat of the day causes the rock to expand, while the cool desert nights contract it. This endless cycle weakens the stone, causing thin layers to peel away, a process called onion skin weathering. Over time, entire chunks of the canyon walls give way, tumbling into the depths below. The result is a breathtaking landscape of towering sheer cliffs, deep gorges, and sculpted sandstone domes. The most striking of these formations, known as the Lost City, resembles an abandoned metropolis, a maze of rounded rock formations shaped by millions of years of wind and water. While erosion has shaped the canyon's form, it is the elements, fire, water, and stone, that define its character. Fire is a part of the land's natural cycle, sweeping across the plateau in periodic blazes. It clears out old vegetation, making way for new growth, and reveals the true resilience of the ecosystem. The spinifex grasslands that cover the canyon's rims are designed to withstand fire, regrowing swiftly after each burn. Water, despite its destructive power, is also the giver of life. In the Garden of Eden, water collects in permanent pools, sustaining pockets of ferns, cycads, and ghost gums. These plants are relics of a wetter past, survivors from a time when the outback was green and teeming with ancient rivers. Wind too plays a crucial role in shaping the landscape. As it sweeps across the plateau, it carries fine grains of sand, slowly wearing away at the rock. Over thousands of years, it carves delicate ridges and etchings into the rock, further refining the canyon's dramatic appearance. The contrast between life and stone is stark, yet it is this very contrast that makes Kings Canyon so breathtaking. Standing at the edge of the rim walk, gazing over the sheer drop into the canyon floor, one can't help but feel the insignificance of human time compared to the eons that shaped this place. Beyond its sheer cliffs and breathtaking gorges, Kings Canyon holds something even more extraordinary: traces of ancient life fossilized within its stone. Throughout the Morini and Carmichael sandstones, fossilized ripples, burrows, and even microbial mats provide evidence of a world long lost to time. These remnants of prehistoric marine environments offer a glimpse into life 500 million years ago, when the region was submerged beneath ancient seas teeming with primitive organisms. They serve as nature's record keepers, preserving a time when life was still finding its way in a vast and evolving planet. Though Kings Canyon appears timeless, it is not frozen in stone. It is still changing, still evolving. The forces that carved it are still at work. With every summer storm, with every gust of wind, the landscape shifts. Cracks widen, rocks fall, sand is carried away to new places, forming the next chapter in this endless geological story. One day, far into the future, Kings Canyon as we know it may disappear. The mighty walls may crumble, the Garden of Eden may dry up, and new landscapes may rise in their place. But even as it changes, it will always remain a monument to the unimaginable power of time, a place where the earth has inscribed its own history into stone. For those who walk its trails, for those who stand upon its rim, Kings Canyon is more than just a canyon. It is a window into deep time, and a humbling reminder of nature's grand design. It is, and always will be, a cathedral of stone, standing in silent reverence to the forces that shaped it. And though we may marvel at its beauty today, it is only a moment in the canyon's long and ever-unfolding story. As we gaze upon its walls, we do not just see rock, we see time itself, written into sandstone, whispering the secrets of the past and the promises of the future. Hope you found this as interesting as I did, and as always, thanks for watching. There's something interesting when you open up GeoVic, apply the golden base metal layer, and look at Heathcote. Amidst the sea of yellow coloured areas that signify known gold deposits, we have this tan colour, an enrichment of chromium and gold that is only found in this area. So what happened here that differentiates it from the rest of Victoria? To unravel this mystery, we must journey back through time, to an era where the Earth's crust was restless, and great geological upheavals shaped the land we now stand upon. The story of Heathcote's chromium and gold enrichment is not a simple one. It is a tale of volcanic eruptions, oceanic subduction, and the relentless forces that shaped the landscape over hundreds of millions of years. Don't forget to click on that subscribe button, hit the bell icon, and like this video, as it's the best way to support this channel. And if you enjoy it, consider sharing it around. The Heathcote region, home to the Heathcote Greenstone Belt, holds the key to this enigma. The formation is primarily composed of pilobasalts, andesites, bonanites, dolerites, volcanic sandstones, rhyolites, tuffs, black shales, and cherts. These rocks tell the story of a marginal sea, an ancient basin formed through rifting at the leading edge of the Australian continent during the Cambrian period, 541 to 485 million years ago. This marginal sea formed in a back arc basin setting, where oceanic crust was actively spreading due to subduction further east, beneath a now buried volcanic arc. Bonanite, a rare volcanic rock type found in Heathcote, is particularly significant. These high magnesium, silica-rich lavas typically form in forearc settings above subduction zones, but their presence in Heathcote suggests a different process. In this case, the bonanites formed in a marginal sea or back arc basin setting, where subduction-driven extension led to high degrees of mantle melting. The combination of fluid influx from the subducting slab and rifting-induced decompression melting created conditions similar to those of a forearc, allowing bonanite magmas to erupt in an otherwise back arc environment. These lavas are known for their chromium and nickel enrichment, key indicators of their mantle-derived origins. As bonanitic magma erupted onto the seafloor, it carried with it chromium, a metal that crystallized within its matrix. Over time, these volcanic rocks were altered by tectonic movements and hydrothermal fluids, which later played a crucial role in introducing gold. The metamorphism of the Heathcote Greenstone Belt primarily took place during the Cambrian to early Ordovician, 510 to 480 million years ago, when the belt underwent low-grade burial metamorphism, transitioning into prehnite pumpelliite facies in the northern and southern segments, and lower greenschist facies in the central segment. The latter produced mineral assemblages, including actinolite, chlorite, albite, quartz, and epidote, further altering the volcanic lithologies. Later, during the Devonian, 370 to 360 million years ago, regional granitic intrusions led to localized contact metamorphism, producing albite epidote hornfels and hornblende-hornfels facies. The volcanic arc responsible for this subduction-driven spreading system was likely located further east of the Heathcote Greenstone Belt, possibly now buried beneath younger sedimentary cover in southeastern Australia. Some remnants of this arc may exist beneath the eastern Lachlan Fold Belt, including the Melbourne Trough and the Great Dividing Range region, where deeply buried and metamorphosed volcanic sequences are present. The collision of Tasmania with Victoria during the Paleozoic, 450 to 440 million years ago, during an event known as the Benambran orogeny, may have played a crucial role in separating the volcanic arc from the back arc basin. As Tasmania was accreted to the Australian continent, compressional forces could have displaced the arc eastward, effectively splitting it from the back arc system that hosted the Heathcote Greenstone Belt. The collision of Tasmania with Victoria played a fundamental role in mountain building processes across Victoria. The intense compressional forces thickened the crust, causing widespread folding and thrust faulting. The uplift of these fault-bounded regions contributed to the formation of mountainous terrains, resembling the modern-day South Island of New Zealand, where active compression is currently forming steep mountain ranges. As the crust thickened, the deep burial of rocks resulted in further metamorphism and granitic intrusions. These granites, which intruded into the already deformed landscape, not only contributed to the metamorphism of the surrounding greenstones, but also added further uplift and structural complexity to the region. Though these mountains have since eroded over millions of years, their remnants remain preserved in the highly folded and faulted rock sequences seen today in the Lachlan Fold Belt. But the story does not end with volcanism. The Earth is a restless artist, constantly reshaping its creations. During the tumultuous periods of orogenesis, when vast mountain ranges were thrust skyward, fractures and faults splintered the landscape. It was along these wounds in the Earth that hydrothermal fluids, infused with gold from deep within the crust, surged and swirled. These fluids, heated by the infernal depths of the planet, reacted with the existing bonanitic and basaltic host rocks, precipitating gold in unlikely companionship with the chromium that had slumbered there for eons. Gold and chromite are unlikely bedfellows. The one, a noble metal, is known for its malleability and radiance. The other, an oxide of chromium, is an industrial titan, a mineral of steel and strength. Yet here in Heathcote, they exist side by side, a demonstration to the sheer complexity of geological alchemy. The processes that brought them together are both ancient and ongoing, a saga written in fault lines, mineral veins, and the unseen pressures of the Earth's interior. The Heathcote Greenstone Belt is structurally divided into three segments. The northern and southern portions exhibit characteristics of disrupted ophiolite sequences, while the central segment, hosting the Mount Camel Copper Show, is thought to be of rifted oceanic origin. A disrupted ophiolite sequence refers to a fragmented and structurally deformed remnant of ancient oceanic lithosphere, typically thrust onto a continental margin during tectonic collisions. Ophiolites consist of deep-sea sediment, basaltic pillow lavas, sheeted dikes, and ultramafic rocks derived from the Earth's mantle. When these sequences are disrupted, they are often broken up by faulting, shearing, and metamorphism, making them difficult to recognise in their original stratigraphic order. The presence of these disrupted sequences in Heathcote suggests that parts of the region once belonged to an oceanic crustal fragment that was later deformed and incorporated into the evolving Lachlan Fold Belt. The marginal sea setting best explains the primary formation of the Heathcote Greenstone Belt, rather than a direct subduction-related volcanic arc. Geochemical evidence indicates that the metabasalts and metadolerites of the Heathcote Belt align more closely with mid-ocean ridge basalt compositions rather than those of island artholites. The structure of the Heathcote Greenstone Belt is vividly visible in magnetic surveys, where it stands out as a bold, linear anomaly against the surrounding geological features. This distinct signature is due to the high iron and mafic mineral content of the belt, a direct result of its volcanic and intrusive origins. Magnetic data not only highlights the continuity of the belt, but also reveals the intricate fault systems that divide it into segments. These major fault lines, which slice through the belt like deep geological scars, have played a crucial role in shaping its present-day structure and controlling the pathways for hydrothermal fluid movement, influencing mineralization patterns. What was once a thriving submarine volcanic system, teeming with molten lava and seafloor hydrothermal vents, is now a deeply folded and fractured geological relic. The once glassy basalts have recrystallized, the copper-rich gossans have weathered into iron-stained outcrops, and the subterranean fractures remain as silent conduits, channeling the whispers of past orogenic events. Today, Heathcote's unique mineralization beckons explorers and geologists alike, its chromite serving as a signpost pointing toward untapped riches below. The echoes of ancient magmatic intrusions still linger beneath the surface. Could Heathcote be more than a historical curiosity? Could it, in fact, be the gateway to a new frontier of resource discovery in Victoria? The presence of both chromium and gold in this single, isolated location can only be explained by an extraordinary sequence of events, a perfect storm of geological conditions that never repeated elsewhere in Victoria. The primal birth of bonanitic and basaltic volcanic rocks, the shattering impact of colliding continents, the ceaseless flow of mineral-rich fluids through fractures in the earth, all of these elements conspired to make Heathcote an exception to the rule. To understand Heathcote, before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.